Right, what I'd like to do now is change gear, so to speak. We're going to bring the tests right up to date. In other words, by up to date, I mean these tests have been developed, if you like, over years and years of looking at closed-loop control vehicles. And the purpose of this is to evaluate completely the entire engine management functionality with just two simple inputs. The two inputs we're going to look at are air mass meter voltage. That's a transition from the air mass meter as the engine is driven through what we call a wide open throttle test. And basically what we do is warm the car up fully, obviously for safety, ensure that it's fully enclosed loop, lambda sensor is completely active, and basically we bury the throttle pedal on the floor. We get a full profile output from the air mass meter. We lift off, and the time period we conduct that test is around 2 seconds. We also then add to that the actual output from the lambda sensor. Now this confirms then precisely across that wide open throttle exactly what's happening to the fueling. And of course lambda sensor reports oxygen content in the exhaust. The purpose of this is if there's any anomalies with combustion, and I use the word anomalies rather than misfire because anomalies could be poor injection spray pattern, inadequate delivery, poor fuel flow, air ingress in the fuel supply, cavitation as we call it. So any anomaly at all with ignition or fueling is actually reported back from the lambda sensor across the wide open throttle test. So let's do a bit of talk and chalk on the board, explain how we're going to set the profile of test up, what the trigger is, why it's placed in such a position, and then we'll conduct the test for real. So let's just take a look at the flip chart. First of all, the air mass meter is essentially a 5-volt component. At idle we'll have somewhere around 0.8 to 1 volt. So we'll have a fairly smooth transitional output. When we initially open the throttle, we get a transient increase in voltage. That's the initial increase in airflow across the sensing element. This produces an initial transient peak. We then have, in effect, we actually have then a drop of pressure. We go from a negative pressure in the manifold to atmospheric pressure, and we get a lean void. In other words, we get a moment's pause or hesitation in the flow of air across the sensor. So we get a drop. Then as the engine increases speed, the air increase across the air mass meter then reports back an increase in voltage up to a peak maximum. And we're going to talk about the actual value of this as well. This is very, very important. We then lift off, and we get, in effect, closed throttle and a rapid reduction of flow of air across the air mass meter. The signal drops rapidly. Two things then happen. The idle air control device, in this case a stepper, well it's actually drive-by-wire, so it's actually a drive-by-wire throttle control, kicks in suddenly, so it's got to capture the engine. But we also have a recirculation valve, because this is a turbocharged car, and the recirculation valve then opens to release all that compressed air in a recirculation back into the intake. So in our case we'll get a secondary spike here through recirc, and then a gradual smoothing off back to natural idle. That's what I expect to see. The peak voltage, this point here, is absolutely critical. If this air mass meter is functioning correctly, we should have 4.7 volts. Any less than that, we're going to have potentially a lean car. We have obviously a threshold somewhere around 4.5 to 4.7 is okay. So I would expect to see 4.7, so we can measure that on the screen. After this, we're going to then add lambda. Now I'm going to save the explanation of lambda because I want to conduct this test first. I also want to set a trigger up. The trigger is the device which stabilizes this image or captures this image on screen for us. And I want to set a trigger up so that it's actually sat there waiting. In effect, I don't want any image to be displayed on the screen until we actually open the throttle. That means that this test can be conducted singularly with no help at all, although I have got David in the car to help. But you can conduct this test all on your own. This is a drive-by-wire car. You cannot increase engine speed under the bonnet. You have to go to the throttle pedal. And indeed, that's where you should increase the engine speed always. So I'm going to set a trigger up with a threshold of around 2 volts. And then what will happen, there is a theoretical hidden trap on the set of crosshairs. When the voltage crosses that threshold, the image will be drawn and captured on the screen. So it's around 2 volts with an offset of about 30% across the screen. So the entire image then is displayed on the screen. So that's what we're going to do. Let's now prepare for that and then conduct the test and then we'll come back to the flip chart and then add lambda. It's also upside down lambda, so that also brings very much up to date the actual component functionality on this vehicle. I think it's important just to add to the comments I've already made that this setup has been achieved in a fully manual format. In other words, I've taken over total control of all the parameters. The three essential parameters that we're speaking about is voltage range, 0 to 5 volts, and that's been set manually from channel A range. Time base. Now time base, the entire duration across the screen is approximately 2 seconds. So the actual time base has been established by a little bit of trial and error. In other words, what I want to see is a large enough image across the screen that's acceptable to me, and this is a personal choice, without being too large or too small. I want to see all the critical events. In other words, are there any anomalies in the signal? And to do that, I want the image probably occupying at least 2/3 of the screen, both in terms of horizontal and vertical dimensions. But it's all been done manually without using any presets from the automotive selection box. So, brief pause and then we'll conduct the test. Right, the first important thing is I need to coordinate with David because he in effect is my throttle pedal. As I say, it's drive-by-wire. I cannot control the throttle from under the bonnet, so I'm going to rely on David. It's important that the car is fully warmed up. We've taken some time out of camera to actually warm the car up, and the reason for that is that the lambda sensor must be completely active because this is a vital component of fuel control, and without that being active we're not going to get an accurate report of what's actually taking place in the exhaust pipe. Bear in mind, the lambda sensor on this car is broadband, which means it's upside down. Therefore, the voltage transition when it's rich is in the low region, which is completely the opposite of the normal Zirconia dioxide sensor. So we're warming the car up. I'm just going to check that we haven't pre-triggered on the scope. So we're starting with a clean screen, waiting for the first sample from the air mass meter. What we've done is we've conducted a few sample tests. Sometimes you get what we call pre-triggering due to noise. Noise can be caused by ignition, induction interference, if you like, into the probe. So try and keep your probe well away from ignition. If you do get a bit of pre-triggering, all you need to do is 3 or 4 samples from the air mass meter and select the frame or the sample on screen which you're happy with. So I'm going to ask Dave now to conduct a full wide open throttle test, and let's see the profile. Thank you, Dave. I'm going to ask him to switch off now, and we've got an ideal profile. Let's discuss what we've got in detail. Right, as predicted, you might be interested, this little anomaly here, the actual idle voltage, if you like, has this erratic appearance and profile. In actual fact, diagnostically that's actually quite useful because it represents the turbulence of the airflow across the sensing element in the air mass meter, which now on surface mount technology can actually respond within 1 millisecond. So it's a very accurate indication of the mechanical efficiency of valves and camshaft performance. So any irregularities in that could suggest a problem with valves, timing, sticky valve, tappet problems. That's quite repetitive, so I'm fairly happy with that. We then come across to the point, the initial take-up of throttle. This little primary peak represents the initial opening of the throttle, increase in airflow across the sensing element. We then get this low void that I explained on the flip chart, where the negative pressure in the manifold is very quickly turned into atmospheric pressure. Then we get a rapid increase in airflow, so that in effect there's a slight hesitation in the amount of air passing the air mass meter at that point, the transient throttle position. We then get a rapid increase in airflow right up to a peak voltage, and we've actually got 3.54. We've just topped 4 volts there, but then again it depends how hard you rev the engine, so there's a bit of common sense applied here. I'm not too worried you haven't reached 4.7 yet because we've not yet added the lambda sensor. The lambda sensor is going to add this next part of the equation. Is this car rich or lean during this transient throttle test? And the proof will be in the moment when we connect lambda to this test. We then lift off a very rapid reduction in voltage because now the throttle disc is closed. Now we didn't get this little recirc peak, and the reason for that is that we didn't actually reach full turbo boost on that. You've got to imagine that the turbo needs time to spool up. If we don't work the turbo hard, we've not got the same positive pressure in the intake, therefore the recirc valve doesn't respond, it will stay closed. This is controlled now, it's three-dimensional mapping, and whether the recirc valve opens or not depends upon the positive pressure on the intake system. So those are the reasons why we've not got quite the same images on the board, but nonetheless I've got a perfectly accurate and detailed response from the air mass meter, and I can conclude from that, from the profile, that this air mass meter is absolutely spot on. It's working quickly, it's responding very, very quickly to the opening of the throttle, and we're going to prove this with lambda in a few moments. And of course, this hesitation here, this recovery, increase in voltage is where the electronic throttle motor responds to the engine speed dropping and picks the throttle up, and then will eventually recover the engine speed back to that voltage. In other words, as the throttle disc adopts the correct idle position, we'll end up with that predictable voltage back at natural idle. So let me now add the second channel. We'll do some talk and chalk, add the second channel, and then connect channel B to the broadband sensor, and then we'll see what response we get from that. Right, let me first explain some very important differences between broadband and traditional zirconia dioxide sensors. Broadband sensors actually work on current transition for the control of the air-fuel ratio. However, if it's a 5-wire broadband, and this one is, there's a red or pink circuit which actually displays a voltage transition in a very similar way to a traditional 0 to 1 volt lambda sensor. Now, it doesn't display this transition between 0 and 1 volt, it's actually between 2.5 and 3 volts. The reason for that is that there are two sensing elements in a broadband sensor. One is supplied with 2.5 volts as a reference and one with 3. So the actual transition takes place between those two references. So what you're going to get, in effect, if we cruise the engine, is a cyclic output, a little bit slower but similar to a traditional sensor, with the range between approximately 3 volts and 2.5. That's also upside down, so I'm now going to overlay the anticipated image on our trace. So let's say that the sensor's cycling in a normal manner. Along comes the wide open throttle test. I would expect it very quickly to go rich, stay rich, suddenly go lean, and then start to respond. And the total amplitude of that, as I say, is within this narrow range between about 2.5 and 3 volts. This part of the signal should then indicate very clearly that through this wide open throttle profile the engine is actually rich of normal, which is what we'd expect to be. And of course we can determine the sensors responding quickly, in other words it's an active and accurate sensor, by its recovery time here. Because on overrun the injectors are turned off, which means lots of oxygen in the exhaust, no fuel, therefore the voltage should go high. I am lean. So that's the anticipation. Let's see what we get in real life. I'm going to connect to the pink circuit on the broadband sensor, which is on the top left of the bulkhead, and I'm going to use this piercing probe, which has two functions really. By pulling back the shroud, we expose a steel pin. That very neatly holds the cable in position, and then by screwing in that bezel, it then locks that firmly in place. So it's a hands-free interface within the circuit, which is important, and it causes minimal damage to the conductor. So I'm going to use that probe in this case. Fortunately, this probe is quite easily attached to the cable. It's quite accessible, and we need channel B. Connected to the broadband sensor. And of course we do need a ground reference as well, and we have sufficient lead to go back to the battery ground, I would think. Ground reference attached, and I'm going to use a skyhook again because I don't want to collect noise in this probe, so by keeping it away from ignition we should reduce the amount of induced noise in the probe. That's the connection done, and now we're going to set up the scope to a compass so we can encompass this voltage range between 2.5 and 3 volts. Okay, we've now set up this second channel on the broadband sensor on the pink cable, which gives us this transition in voltage. And just to recap, we're expecting a negative voltage transition during the enrichment range. So let's now reconfigure the test on the vehicle. Wide open throttle test again. This time 2 traces will appear, a repeat of the original air mass meter, and the second trace, channel B, will be the transition of voltage from the broadband sensor. And then we'll switch the car off and then discuss in detail what this image actually does for us diagnostically. Thank you, David. Okay, let's take a look. Absolutely textbook trace. If you don't get this image first time every time, because a lot of this depends on how you open the throttle, whether there are any noise spikes in the signal, so you might get some transient mistriggering during this test, but it's an absolutely superb test. We've looked at the voltage output from the air mass meter. That confirms the air mass meter is working. That's fine, but we don't know if the engine's actually being fueled correctly, or indeed if there's any ignition anomalies during the wide open throttle test. Let's take a look at the voltage. The red trace, channel B, now you notice that the trace is actually flat. Now, for a broadband sensor that controls current as the input, if you like, to the PCM, a 0 change in current means lambda 1. So to see a flat line is actually perfect air-fuel ratio. However, when we operate the throttle, clearly fueling is going to change, and what happens is we get a very rapid transient, negative transient, I am rich. We get a momentary lean period, or it starts to go lean, and then very quickly goes back rich. So I'm fairly happy that during this wide open throttle period we have a rich of normal mixture. Now look at the transition here. I explained that when you close the throttle down rapidly, you have an enormous amount of oxygen in the exhaust, and just look how this sensor's responded. It's absolutely textbook vertical climb indicating rapid response, so the actual sensor is extremely active and accurate. In other words, it's not an aging sensor that's faulty and slow to respond. And of course, off trace we can't see the recovery, but the recovery would then come back down to a fairly neutral voltage, as I say, between about 2.5 and 3 volts. Your scales down here, we came in at about 2.3, which is about the average voltage, so it's between about 2.5 and 3 volts. So absolutely textbook result. And you notice also, once again, we've got the throttle body idle control kicking in as well to correct the idle speed. So absolutely textbook case. It's a crucial test. We use this test on every single vehicle that comes through our workshop because it's the final confirmation test that not only are the air mass device working, that the fueling of the engine, the ignition profile, the ignition performance is absolutely correct. The only test we do after this is simply a gas test at the exhaust pipe just to conclude the catalyst is working correctly. So it's a really critical measurement that we make, and one we rely on a great deal. It also demonstrates the great versatility of the scope, because to be able to manipulate the tool to carry out these tests, in other words, these are user-defined tests. This is a test that I want to carry out. I'm not being restricted in the way I use the tool. The tool has the presets if I wish to go in quickly and select a preset. It also gives me the flexibility to use any of the tools on any of the channels in any way I want. So it's a tool that's ideal for the beginner. It's a tool that's ideally suited for the expert professional who knows exactly what he wants to do and produce some of these really bespoke tests. And this is one that we've developed over a number of years. So can't really say much more. It's a superb tool to use.